Okay, so the next thing I'm going to talk about is true flow. And I'm going to talk about true flow in 2D. I don't have any examples of true flow in 3D, but I'm going to show you what the ramifications of this will be, I think, in the future. So what you can do to get true flow in 2D is to actually split the aperture of an ultrasound array. So you can scan from the right side, steering from the right to left, and then you can scan from the left side, steering from left to right. And in the middle, you end up with two measurements of the velocity at every position. That means you can orthogonalize it into x and y and produce a lateral and axial velocity at every position. You can either do this by receiving from the same apertures that you're sending from, or you can always receive from the center aperture as well. But the ultimate result is the same. And here's an example of this. This is a rotating disk which contains scatterers, and as you'd expect, the beam is being steered from left to right, and the disk is rotating counterclockwise, so the right side is going to look red, and the left side is going to look blue just because of the rotation. Now this is a 2D rotation, as this phantom is rotating on a central axis. So you can, like I said, you can steer towards the left, and you get this image, and then you can steer towards the right, and you get this image, and then all you do is combine them, and then what you end up with is the x component, which is transverse, so these guys are all going that way, and these guys in the far field are going that way, and you can do the axial, or the axial image, so those guys going up there and down there. You'll notice we're actually losing some of the lateral components. That's because we can't steer the beam enough to see from points up here from two directions. However, in the area that you can see it, you can definitely get the true 2D velocity. Remember, the third component, there's no z component or out of plane component here. And this is what this looks like. You can resolve the velocity components at every position, and this is very much what one would expect to see. As you get further from the axis of rotation, these vectors get longer because the radial velocity gets longer as you move away from the axis of rotation. Now, some of this may be a surprise to you all because no one does this, mostly because the applications are very limited and not particularly interesting. However, if you could do it in 3D, you could produce pictures like this. Now, this is not a true velocity image. These are images that I got off the web, and these are power Doppler images, so they have no directional information. And that because of that, you can get 3D imaging in power Doppler. What you'd like to see in 3D is at every position, you would get the true velocity measurement, the true 3D velocity. That's going to require 3D and 4D sampling. Once you do that, you can get the true 3D velocity. And the consequence of that is you'll be able to see the true velocity at every position and independent of the direction of sampling, but you will also be able to measure pressure gradients, potentially. And that is the huge potential benefit for this. This is a great application whose time may be approaching in the future. But what I'm talking to you now is not available, but the concepts are there. What you would be able to do with pressure gradients is solve to generate a local solution of what's called the Navier-Stokes equation. The Navier-Stokes equation is a very complicated nonlinear differential equation, which is sort of the bread and butter of fluid mechanics people. It basically describes the equation of motion of moving fluids. It's a very tough problem because it's nonlinear. But if you can sample fast enough and dense enough, it may be tractable locally. And if it is tractable locally, if you can solve it at a given position, you could then theoretically measure pressure drops. And by doing that, you'd be able to measure pressure drops without a catheter or contrast agents, and it would be a totally benign measurement. Whereas now, to measure pressure drops, you have to put a catheter or do a catheter procedure. So it's an invasive technique. So what we would be doing is removing a catheter procedure and using a totally benign ultrasound technique. And 3D and 4D can make this happen. Okay, I put this up here not to make people choke because of the differential equation. I just want to show what we would have available if we had real-time 3D and 4D measurements. And this is the Navier-Stokes equation in one direction. There's a similar solution or a similar equation for z, y, and x. This is the x direction Navier-Stokes equation. Okay, rho is density. That's the density of blood. V sub x is the velocity in the x direction. Remember, we have 3D velocities. We have all that information. We know the velocities in the x direction. Since it's real time, we can sample in time, so we can get the rate of change in velocity of the x direction. That's acceleration. So we've got that. Since we've got all the 3D parameters, we know the velocity in the x direction across the blood vessel. So we have velocity in x locally, then we have the local gradient in the velocity of x in position. So we've got that. We've got the velocity in y for the same reason. We can look at the change in the velocity of x in the y direction. We've got this. We can also get the velocity in z because we're sampling in 3D, and we also have the gradient of the velocity of x in the z direction. We've got this. So we've got everything on the left side of the equation by sampling dense enough and fast enough in 3D. Okay, let's look at the right side of the equation. F sub x is what's called a body force. That corresponds to gravity. That has almost no effect on this. We can ignore this. This is the pressure gradient. This is what we want to calculate. So all we then need is this, which is mu is viscosity, and this is what's called the Laplacian of the velocity. This is the second derivative of the local velocity. This is an extremely noisy measurement. This is the second derivative. However, we could sample a very long time. Remember, we're in competition with a technique that would be an invasive procedure. So imagine how long it takes to put a catheter into somebody. You have to bring them into the x-ray room or imaging suite. You have to do it sterilely. You have to clean the skin. You have to put the catheter in. You have to feed it in. You have to put it in the right position and make a measurement. So we have all that time, at least, to do this in a non-invasive way. So it's very possible we can get this parameter as well. We've got all the data. We just have to make sure that we can overcome the noise. We can then solve for the pressure gradient in x. We have to do this for all the other equations. However, remember, this does not have to be done in real time. We're competing with a clearly non-real-time technique. And so this now becomes a potentially viable solution using, if we have true 3D, 4D. Okay, so here's a picture of the stenosis. This is a smooth stenosis. All we care about is right at the stenosis. It might be prudent to sample in 3 dimensions, from 2 directions. That way, if there's any components across the beam, which we can't get Doppler shifts across the field, then we would have another way of sampling it. Now, it's clear that we can do this because there are ways now to do correspondences of images from different orientations. They're very robust, and my guess is that they'll certainly work out to be possible in the future. Okay, so what does this look like? Here's a 2D image, which you're all used to seeing. This is a carotid artery with a stenosis. So what we want to do is we want to measure the pressure drop across this stenosis. Let's assume that we have 3D, 4D imaging. Okay, so what we're going to do is get the velocities at every position. So these arrows are representing the local velocities. The colors don't mean anything. I made them either black or white just for contrast purposes. The lengths sort of correspond to how fast it's going, but we'll have all that information. So now we'll sample it there. It's now getting wider in this position, so it's slowing down. We'll have samples there. Now it's narrowing again. It's speeding up. It's still speeding up. Now it's spreading out again, slowing down. Now it's slowing down because we're going further, and there now we're into the normal blood vessel, and so now we've got all the velocities sampled across that stenosis. Okay, so now what we do is measure the pressure drop or the pressure gradient at every position. We'll measure it there, and then we'll measure it there. Remember, we've got all that information. We'll measure it there, we'll measure it there, we'll measure it there. And then all we'll do is integrate these pressure gradients. So you take basically the sum of the gradients across here multiplied times delta x, and we'll do it across here. This is a standard integration procedure across these planes. Remember, we have all of these planes as a function of position. That gives us the pressure drop. So now we have the delta L is the length of the stenosis. So we have now delta P across that stenosis. We have the pressure drop. This is done in a totally benign method. Voila, pressure drops. Each time this is done, it requires one fewer interventional procedure. And ultrasound, hopefully and possibly in the future, will be able to do this using 3D and 4D imaging. So thank you very much.